Linear Algebra II, Tutorial 6, Euclidean Spaces, Part 2. Problem 1. Find the distance in the Euclidean space E3 from the vector v with coordinates 1, 2, 0 to the subspace M of E3 generated by the vector w with coordinates 1, 1, 1. Solution. The distance from a vector to a subspace equals the length of the orthogonal projection of this vector onto the orthogonal complement of the subspace. However, note that since the dimension of M is equal to 1, so M is generated by one non-zero and hence linearly independent vector, 1 is smaller than 2. And 2 is equal to 3 minus 1, so 3 is a dimension of E3 and 1 is a dimension of M. So 2 equals the dimension of the orthogonal complement to M. So the dimension of M is strictly smaller than the dimension of the orthogonal complement to M. So it is much easier to determine the orthogonal projection of V onto M. And then, when we know that, we can determine the orthogonal projection of V onto the orthogonal complement to M as V minus the orthogonal projection of V onto M. Now, to determine the orthogonal projection of V onto M, we need an orthonormal basis in M. So we have a basis in M consisting of the vector W. So this vector spans M and it's non-zero and hence linearly independent. So now we can simply use the very easy version of Gram-Schmidt's method. To get an orthonormal basis of M, we only need to norm the vector W. So we take the vector W and divide by its length. And the obtained vector will be denoted by U. So the vector W is 1, 1, 1. So the scalar product of this vector with itself is 1 square plus 1 square plus 1 square. So its length is the root of 3. So the outcome is the vector 1 divided by the root of 3 times 1, 1, 1. This vector forms an orthonormal basis in M. Now, to determine projection onto M, we can just apply the standard formula. So we have an orthonormal basis in M. So the projection of the vector V onto M is equal to the sum of the orthonormal basis elements with the coefficient, the scalar product between our vector and the element. And we have only one element, so the formula is the scalar product between V and U times U. Well, we also know that U is W divided by the length, so we can rewrite this formula as W times the scalar given by the following fraction. In the numerator, we have the scalar product between V and W, and in the denominator, we have the scalar product between W and W. The vector W is 1, 1, 1. The vector V was 1, 2, 0. So we have 1, 1, 1. In the denominator, we have 3. We already computed the scalar product between W and itself. And the scalar product between V and W will be 2 plus 1 plus 0, which is also 3. Consequence, the projection of our vector V onto M is the vector 1, 1, 1. So now we can determine the projection of V onto M orthogonal complement. For this, we just take V and subtract the projection of V onto M. So we take the vector 1, 2, 0 and subtract 1, 1, 0. The outcome is the vector 0, 1, minus 1. And so the distance from the vector V to our subspace M is the length of the orthogonal projection of V onto the orthogonal complement to M. That is the length of the vector 0, 1, minus 1. And this length is equal to the square root of 0 squared plus 1 squared plus minus 1 squared, which is the square root of 2. So the answer to our problem is the distance from V to M is the square root of 2. This completes problem 1. Problem 2. Determine the matrix in the standard basis for the linear operator f from E3 to E3 given by the reflection with respect to the plane n orthogonal to the vector v with coordinates 1, -1, 1. Solution. Recall that the matrix of the linear operator in standard basis is given as follows. So the first column of this matrix consists of the coordinates in the standard basis of the image of the first standard basis vector E1 under our linear operator. The second column consists of the coordinates in the standard basis of the image of the second standard basis vector under our linear operator. And similarly, the third column consists of the coordinates in the standard basis of the image of the third standard basis vector under our linear operator. So we need to compute these three coordinates. Note that if we take any vector x in our space E3 and write it as a sum of the orthogonal projection of x onto n plus the orthogonal projection of x onto n orthogonal complement, then the image of x under our reflection f is equal to the sum of the projection of x onto n. The first summand is the same, but the second summand changes the sign, minus the projection of x onto the orthogonal complement. So this is how the reflection works. The elements in n stay on their places, while the orthogonal elements change the sign. So in order to solve the problem, we need to determine such decomposition for each standard basis element E1, E2, and E3. So we need the projection of E1, E2, and E3 both onto n and onto the orthogonal complement of n. And by the definition, the orthogonal complement of n is spanned by the element v, and v is a non-zero vector. So v forms a basis in an orthogonal complement. And similarly to the previous problem, it follows that for any vector x in E3, the projection of x onto the orthogonal complement to n is given by the formula the vector v times the scalar given by the fraction with the numerator, the scalar product between x and v, and the denominator, the scalar product between v and v. So we use this formula to compute the projections onto the orthogonal complement to n of the vectors E1, E2, and E3, and then to compute all other ingredients which are necessary to solve the problem. So here is a computation for the vector E1. The projection of E1 onto the orthogonal complement to n is given by the vector v, which is 1, -1, 1, times the fraction where the denominator is 3, so this is the scalar product between v and v, so this is 1 square plus -1 square plus 1 square, and then the numerator is the scalar product between E1 and v, which is 1 plus 0 plus 0, so this is 1. So this projection is 1/3 of 1 -1, 1. So the other projection, the projection of E1 onto n, is then given as a difference between E1 and the projection onto the orthogonal complement to n. So this is a vector 1, 0, 0 minus 1/3 of 1 -1, 1. And this is a vector 1/3 of 2, 1, -1. So now we have the decomposition. This is a projection onto orthogonal complement. This is a projection onto n. So f of E1 is equal to the following thing. We take the projection onto n, and we subtract the projection onto the orthogonal complement. So we have 1/3 of 2, 1, -1 minus 1/3 of 1, -1, 1. So this is equal to the following. So we have 2/3 minus 1/3, it's 1/3. 1/3 plus 1/3, it's 2/3. And -1/3 minus 1/3 is -2/3. So f of E1 is the vector 1/3 of 1, 2, -2. Now let us compute for E2. The projection of E2 onto the orthogonal complement is given by our vector v, which is 1 minus 1, 1, times the following fraction. The denominator is 3, it's the same as in the previous case. And the numerator is a scalar product between e2, which is 0, 1, 0, with the vector v. So it's 0 minus 1 plus 0. It's minus 1. Now the projection of e2 onto n is e2 minus the projection of e2 onto the orthogonal complement. So this is 0, 1, 0 minus 1/3. So it's plus 1/3 times 1 minus 1, 1. So it gives us 1/3, 3 minus 1, 2/3, and then 1/3. This is the outcome. And now we can again compute f of e2. We take projection onto n and subtract projection onto the orthogonal complement. So projection onto n is 1/3 of 1 to 1. Projection onto the orthogonal complement is minus 1/3, 1 minus 1, 1. So we should write plus 1/3, 1 minus 1, 1. So 1/3 plus 1/3 is 2/3. 2/3 minus 1/3 is 1/3. 1/3 plus 1/3 is 2/3. So f of e2 is 1/3 of 2, 1, 2. And finally, the computation for e3. The projection of e3 onto the orthogonal complement to n is the vector v, 1 minus 1, 1, with the coefficient given by the fraction, where the denominator is 3, just as in the previous cases, and the numerator is 0 plus 0 plus 1. This is a scalar product. It's 1. So the projection of e3 onto n is equal to e3 minus the projection onto the orthogonal complement to n. So it is 0, 0, 1 minus this vector, 1/3 of 1 minus 1, 1. So it gives us minus 1/3, 1/3, and here's 3 minus 1, 2/3. Consequently, f of e3 is equal to the projection of e3 onto n minus the projection of e3 onto n orthogonal complement. So we take 1/3 of minus 1, 1, 2, and we subtract 1/3 of 1 minus 1, 1. And the outcome is what it's minus 1 minus 1 minus 2/3, 1 plus 1, 2/3, 2 minus 1, 1/3. So f of e3 is equal to 1/3 of the vector minus 2, 2, 1. And now we can collect everything into a matrix. So the matrix of f in the standard basis consists of 3 columns. The first column are the coordinates of f of e1 in the standard basis, and so on. So all these coordinates have 1/3 as the scalar quotient, so we take it out. So it's 1/3 of the matrix 1, 2, minus 2, 2, 1, 2, minus 2, 2, 1. A small remark: a reflection in an Euclidean space is an isometry. Therefore, the matrix of f in any orthonormal basis should be orthogonal. And it is easy to check that the matrix which we got here, it's an orthogonal matrix. Indeed, the length of each column is 1. So 1 squared plus 2 squared plus minus 2 squares is 9. The square root of 9 is 3. Divided by 3 is 1. And this we can do for each column. So each column has length 1, and the different columns are orthogonal. 2 plus 2 minus 4 is 0. Minus 4 plus 2 is 0, and so on. It is easy to check that this matrix has orthonormal columns, and hence is an orthogonal matrix. Problem 3. Let U be the subspace of E3 generated by the vectors U1, which is 2 minus 1, 0, U2, which is 1 minus 1, 2, and U3, which is 1, 0, minus 2. Determine the orthogonal projection of the vector V, which is 1, 1, 2, onto the subspace U and the distance between V and U. First solution. Let us find some orthonormal basis in U. For this, we need to find some basis in U, so we write the vectors which generate U as columns and reduce this matrix to some row echelon form using Gauss elimination. So here we can see we have minus 1, so we can kill this 2 here by adding twice row 2 to row 1. So rows 2 and 3 remain the same, and row 1 becomes 2 minus 2 is 0, 1 minus 2 is minus 1, 1 minus 0 is 1. And now we see that row 1 and row 3 are linearly dependent, so we can just delete row 1. We get the matrix minus 1, minus 1, 0, and 0, 2, minus 2. Here we have two leading elements, and these elements are in the first and the second column, which means that the vectors u1 and u2 form a basis in U. Now we can apply Gram-Schmidt's method to find an orthonormal basis in U. According to Gram-Schmidt, we take u1 and we normalize it. So we divide it by its lengths, and the outcome we denote by w1. So u1 is 2 minus 1, 0, and its length is the square root of 2 squared plus minus 1 squared plus 0 squared. So the outcome is 1 divided by the root of 5 times 2 minus 1, 0. On the next step, we first look for the auxiliary vector w2 tilde, which is equal to u2 minus w1 with the scalar product between u2 and w1. Since w1 is u1 divided by the length of u1, we can rewrite it as u2 minus u1 with the coefficient, the scalar product between u2 and u1, divided by the scalar product between u1 and u1. So the vector u2 is 1 minus 1, 2. The vector u1 is 2 minus 1, 0. We know that the scalar product of this u1 with itself is 5. We computed it here. And the scalar product between these vectors is 2 plus 1 plus 0. It's 3. So w2 tilde is u2 minus 3 divided by 5, u1. We can compute this. So this is 5 minus 6 is minus 1. Minus 5 plus 3 is minus 2, and 10 plus 0 is 10, and with the coefficient 1 divided by 5. So now we can just forget this scalar multiple 1 divided by 5 and denote by w2 two tildes the vector minus 1, minus 2, 10. So this vector is orthogonal to w1, and now we just normalize it. So the vector w2 is equal to the vector w2 two tildes divided by its lengths. So this is equal to, so the vector minus 1, minus 2, 10 times 1 divided by the root of minus 1 squared plus minus 2 squared plus 10 squared. So this is 1 divided by the root of 105 minus 1 minus 2, 10. And the vectors w1 and w2 form an orthonormal basis in U. Now when we have an orthonormal basis in U, we can find the projection of any element in our space onto U directly using the formula. So the projection of the vector v onto U is a linear combination of w1 and w2, where the coefficient for w1 is a scalar product between v and w1, and the coefficient for w2 is a scalar product between v and w2. So now we use that w1 is u1 divided by its length. So we rewrite the first summand as u1 times the scalar product between v and u1 divided by the scalar product between u1 and u1, plus, and we use that w2 is w2 two tildes divided by its length, and we have a similar summand for w2 two tildes. So now we can compute this. u1 is 2 minus 1, 0, and the vector v was 1, 1, 2. So the coefficient will have 5 in the denominator, we know this, and in the numerator we will have 2 minus 1 plus 0, which is 1. Plus the vector minus 1, minus 2, 10, the coefficient will have 105 in the denominator, and in the numerator we will have minus 1, minus 2, plus 20, which is 17. If we add these two vectors, we will get 1 divided by 21 times the vector 5 minus 18, 34. In order to find the distance from the vector v to u, we need to find the orthogonal projection of v onto the orthogonal complement of u. So this projection is equal to the difference between v and the projection of v onto u. So v was 1, 1, 2, and the projection of v onto u was 1 divided by 21, 5 minus 11, 34. So when we compute this, we will get 25 minus 5, 16, 21 plus 11, this is 32, and then 42 minus 34 is 8. So we get 1 divided by 21 times 16, 32, and 8. So the distance from v to u is the length of this vector, which is 1 divided by 21 times the square root of 16 square plus 32 square plus 8 square. So we can take out 8 square. With the square root, we will get 8. And here, under the square root, what remains is 1 plus 4 plus 16, which is root of 21. Altogether, we will get 8 divided by the root of 21. And this is the distance from v to u. Now let us solve the same problem in a slightly different way. Second solution. Let us note that u1 and u2 are linearly independent. This is very easy to see looking at these vectors. Hence, the dimension of u is at least 2, and therefore the dimension of the orthogonal complement of u is at most 1. So let us find some bases in the orthogonal complement to u. Note that some element in E3 belongs to the orthogonal complement of u if and only if it is orthogonal to the vectors which generate u. So which means if and only if the scalar product between x and u1 is 0, the scalar product between x and u2 is 0, and the scalar product between x and u3 is 0. So these three conditions we can write as the following system of linear equations. It's a homogeneous system. So u1 was the vector 2 minus 1, 0. So the scalar product between u1 and x is 2x1 minus x2 plus 0 is equal to 0. So the first equation says that the scalar product between x and u1 is 0. u2 was 1 minus 1, 2. So the second equation, x1 minus x2 plus 2x3 is equal to 0, says that the scalar product between x and u2 is 0. And the vector u3 was 1, 0, minus 2. So the third equation, x1 minus 2x3 is equal to 0, tells us that the scalar product between x and u3 is 0. So let us solve the system. We write the matrix of the system, 2 minus 1, 0, 1 minus 1, 2, 1, 0, minus 2, and we reduce it to a row echelon form using Gauss elimination. So first we have this 1. Let's swap rows 1 and 3 in order to get 1 in the position 1, 1. So row 3 becomes row 1, row 2 remains the same, and row 1 becomes row 3. Now we use this 1 to eliminate everything else in the first column. So we subtract row 1 from row 2, and we subtract twice row 1 from row 3. So row 1 remains the same. Row 2 becomes 1 minus 1 is 0. Minus 1 minus 0 is minus 1. And 2 minus minus 2 is 4. And row 3 becomes 2 minus 2 is 0. Minus 1 minus 0 is minus 1. 0 minus 2 times minus 2 is 4. And now we see that rows 2 and rows 3 are the same. So we just delete row 3 and we multiply row 2 with minus 1 in order to have 1 here. So if we do that, we will get the matrix 1, 0, minus 2, 0, 1, minus 4. And here it's very easy to see that we have a non-zero solution given by the vector 2, 4, 1. So 2 plus 0 minus 2 is 0, and 0 plus 4 minus 4 is 0. So the vector 2, 4, 1 is the solution to this system. And since the dimension of the orthogonal complement of u is at most 1, and this vector belongs to this orthogonal complement, it must form a basis there. And then we can norm this vector to get an O and B in the orthogonal complement to u. So the vector b, which is equal to a divided by its lengths, and the length of this vector is 2 square plus 4 square plus 1 square, and then the square root. So 1 divided by the square root of 21 times 2, 4, 1. So now we can directly compute the projection of v onto the orthogonal complement of u, because this is just b times the scalar product between v and b. In other words, it's A times the scalar product between V and A divided by the scalar product between A and A. So, and the vector V was 1, 1, 2. So we have the vector A, which is 2, 4, 1. And then we know that the scalar product of A with itself is 21, so it's in the denominator. And the scalar product between V and A is 1 times 2 plus 1 times 4 plus 2 times 1, which is 8. So this is the projection of V onto the orthogonal complement of U. And the length of this vector is exactly the distance from V to U. So the distance from V to U is equal to 8 divided by the square root of 21 times the square root of 2 squared plus 4 squared plus 1 squared, should be squared here, which is 8 divided by the root of 21. And since we already know the projection of V onto the orthogonal complement to U, it's also easy to find that the projection of V onto U is the difference between V and the projection onto the orthogonal complement. So it's 1, 1, 2 minus 8 divided by 21, 2, 4, 1. And this is easily computed as 1 divided by 21, 5 minus 11, 34. And now we have solved the problem in a different way. And we got the same results. So this completes problem 3. Problem 4. Let W be the subspace of E4 generated by the vectors W1, which is 1, 0, 0, 1, W2, which is 1, 2, 2, 1, and W3, which is 3, 1, 1, 3. Determine some orthonormal basis in W and extend it to an orthonormal basis in E4. Solution. In order to determine an orthonormal basis, we want to apply Gram-Schmidt, and for this we need a basis. So let's determine some basis in W. So let's determine linearly independent vectors among W1, W2, and W3. So we write W1, W2, W3 as columns in a matrix, and we try to reduce this matrix to a row echelon form using Gauss elimination. But we already see here that row 1 and row 4 are the same, so we delete row 4. Row 2 and row 3 are the same, we delete row 3, and we get the matrix 1, 1, 3, 0, 2, 1. So here we have two leading elements in columns 1 and 2. Consequence, the vectors W1 and W2 form a basis in W. Now we can do Gram-Schmidt. So first we normalize W1, so V1 is equal to W1 divided by its lengths. So it's 1, 0, 0, 1 divided by the square root of 1 squared plus 0 squared plus 0 squared plus 1 squared. So it's 1 divided by the square root of 2 times 1, 0, 0, 1. Next we look for the auxiliary vector V2 tilde, which is W2 minus W2 scalar product with V1 times V1, or alternatively it's W2 minus W1 with the coefficient, the scalar product between W2 and W1 divided by the scalar product between W1 and itself. So it's 1, 2, 2, 1 minus the vector 1, 0, 0, 1 with the coefficient, so here we already see that the denominator is 2, and the numerator is a scalar product between these two vectors. It's 1 plus 0 plus 0 plus 1. It's also 2. So V2 tilde is equal to 0, 2, 2, 0. So this is our auxiliary vector V2 tilde. And then V2 is just V2 tilde divided by its lengths. So it should be V2 tilde divided by its lengths. So it's 0, 2, 2, 0 divided by the square root of 0 squared plus 2 squared plus 2 squared plus 0 squared. And this is 1 divided by the root of 2, 0, 1, 1, 0. So the vectors V1 and V2 form an orthonormal basis in W. So this solves the first part of the problem. Now for the second part, we need to extend this basis to an orthonormal basis in E4. Since we want the extension to be orthonormal, the basis elements which we add must be from the orthogonal complement to W. And at the same time, Any orthonormal basis in this orthogonal complement extends V1 and V2 to an orthonormal basis in E4. So let's find an O and B in the orthogonal complement to W. For this, let us first find some basis in this orthogonal complement. Note that an element X belongs to this orthogonal complement if and only if it is orthogonal to the basis in W, which is formed by W1 and W2. And this is equivalent to the following homogeneous system of linear equations. So W1 was the vector 1, 0, 0, 1. So the first equation is x1 plus x4 is equal to 0. This is the equation that the scalar product between x and W1 is 0. The second vector W2 was 1, 2, 2, 1. So its scalar product with x is x1 plus 2x2 plus 2x3 plus x4, which is equal to 0. So let's solve this system using Gauss elimination. So we write the matrix of the system, which is 1, 0, 0, 1, 1, 2, 2, 1, and we reduce it to a row echelon form. So we use this one to kill this one, so we subtract row 1 from row 2. Row 1 remains the same, 1, 0, 0, 1, and row 2 becomes 1 minus 1, 0, 2 minus 0, 2, 2 minus 0, 2, 1 minus 1 is 0. And now we divide row 2 by 2. And row 1 remains the same, and row 2 becomes 0, 1, 1, 0. So here we have leading elements in columns 1 and 2. So we can take x3 and x4 as free variables. Then the first row here gives us the equation x1 is equal to minus x4. And the second row gives us the equation x2 is equal to minus x3. And then we have trivial equations for the free variables. x3 is equal to x3 and x4 is equal to x4. And now we can rewrite this in the vector form. So the left-hand side, which is x1, x2, x3, x4, is equal to x3 times the coefficients 0, minus 1, 1, 0, plus x4 times the coefficients minus 1, 0, 0, 1. Consequence, the vectors a1, which is 0, minus 1, 1, 0, and a2, which are minus 1, 0, 0, 1, form a basis in W orthogonal complement. If we look at these two vectors, we see immediately that they are orthogonal to each other. So to get an O and B, we only need to norm them, so we divide them by their lengths. So the vector v3, the second vector in our O and B, will be a1 divided by the lengths. So it's a vector 0, minus 1, 1, 0, divided by the square root of 0 plus 1 plus 1 plus 0. So it's 1 divided by the square root of 2 times 0 minus 1, 1, 0. And the second vector, v4, is a2 divided by the lengths, so it's minus 1, 0, 0, 1, divided by the square root of 1 plus 1, which is 2. So it's 1 divided by the square root of 2, minus 1, 0, 0, 1. So the vectors v1, v2, v3, and v4 form an orthonormal basis in W. And this completes problem 4. Problem 5. Let V be a subspace of E3 generated by the vectors E1 minus E3 and E2 plus E3. Determine the matrix of the orthogonal projection onto the orthogonal complement to V in the standard basis. Again, orthogonal projection, if we want to compute it, we need an O and B. So let us find some basis in the orthogonal complement to V. An element X belongs to the orthogonal complement of V if and only if the scalar product between X and E1 minus E3 and the scalar product between X and E2 plus E3 is 0. So this is equivalent to the following homogeneous system of linear equations. The scalar product between x and e1 minus e3 is x1 minus x3. This should be 0. And the scalar product between x and e2 plus e3 is x2 plus x3. It should be 0. And here one can directly guess a non-zero solution. So the element 1 minus 1, 1 is a solution to the system. So if we plug in 1 minus 1, 1 instead of x1, x2, x3, we see that we will get 0 in both cases, so the vector u, which is 1 minus 1, 1, solves the system. Note that the vectors e1 minus e3 and e1 plus e3 are obviously linearly independent. Hence, they form a basis in V. Therefore, the dimension of V is equal to 2, and so the dimension of the orthogonal complement to V is equal to the difference between the dimension of E3 and the dimension of V, which is 3 minus 2, which is equal to 1. And so we can conclude that our non-zero vector u, which belongs to V orthogonal complement, forms there a basis because the dimension of this orthogonal complement is 1. To get an O and B in this orthogonal complement, we just norm our vector u to get the vector v, which is equal to u divided by its norm. This is 1 divided by the square root of 1 squared plus minus 1 squared plus 1 squared, which is 1 divided by the square root of 3, times the vector 1 minus 1, 1, which is our vector u. And now, to determine the matrix of the orthogonal projection onto the orthogonal complement, we take elements in the standard basis E1, E2, and E3 and use the projection formula to compute the images under the projection. So the projection of E1 onto the orthogonal complement is, by the projection formula, V times the scalar product between E1 and V. And we can rewrite it as U times the fraction where the numerator is a scalar product between E1 and U, and the denominator is a scalar product between U and U. The vector U is 1 minus 1, 1. The scalar product of U with itself is 3, we saw it here. And then the scalar product between E1 and U is 1 plus 0 plus 0, it's 1. So the outcome of the projection of E1 onto the orthogonal complement is 1/3 times 1 minus 1, 1. Similarly, we compute the projection of E2 on the orthogonal complement. It's V times the scalar product between E2 and V, which is U times the scalar product between E2 and U divided by the scalar product between U and U. So U is 1 minus 1, 1, the denominator is 3, and the numerator is 0 plus minus 1 plus 1, it's minus 1. And for the third vector, this projection is also given by V times the scalar product between E3 and V, which is U times the scalar product between E3 and U divided by the scalar product of U with U, and this is 1 minus 1, 1, with the coefficient 1 divided by 3. Now we can write these three vectors as columns in the matrix, and we get that the projection onto the orthogonal complement of V in the standard basis has the following matrix. It's 1/3 of the matrix 1 minus 1, 1, minus 1, 1, minus 1, 1, minus 1, 1. And this completes problem 5. Here are some other problems and questions. Question 1. Find the distance in E3 from the vector E1 minus E2 minus E3 to the subspace M of E3 generated by the vector E1 plus E2 plus 2E3. Question 2. Let N be the subspace of E4 given by the equation x1 minus x2 plus x4 is equal to 0. Determine the orthogonal projection of E4 onto N. Question 3. Let V be the subspace of E4 given by the equation x1 minus x2 minus x3 minus x4 is 0. Determine the orthogonal projection of E3 onto the orthogonal complement to V. Question 4. Find the matrix in the standard basis for the reflection in E3 with respect to the plane given by the equation x1 plus 2x2 minus x3 is equal to 0. And question 5. Find the matrix in the standard basis for the orthogonal projection onto the subspace of E4 generated by the elements E1 minus E3 minus E4 and E2 plus E3 plus E4. Thank you very much and see you next time.